This is section 2A, part 2. We've now got our analytic formula, our definition of the derivative, and we'll practice using that in a couple of examples. So in this next one, we have the desire to find f prime of x, the derivative, for the function f of x equals 4 over x squared. And then we'd like to use that to find the equation of the tangent line at the point where x equals 1. So let's see here. I know that f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. And then I'm just going to start plugging in what this means when my function is 4 over x squared. So I replace the x with x plus h, and I'm going to have 4 over x plus h squared minus f of x itself, which is 4 over x squared. And then I'm going to show you a little trick here that I like to use a lot, and you'll see me use it a lot. I really recommend it. If I were to put all of this over h, of course I would create a complex fraction, and complex fractions aren't a lot of fun to work with mathematically. So when this happens to me, what I usually do is I usually say, let's just change this right now, and instead of division, let's write this as multiplication by the reciprocal. So I'm going to take all of this, which is really my numerator, and then instead of dividing by h, I'm going to say let's multiply by the reciprocal, 1 over h. Okay? And again, I do that a lot when I'm working with complex fractions. All right, so let's see here. This, if h is 0, would be 4 over x squared minus 4 over x squared, which would be 0. And that's got a 0 in the denominator. So we really are in that indeterminate form. 0 over 0 again, telling me I probably want to do some algebra. In this case, since I've got two fractions being subtracted, the usual algebra there is to get a common denominator. So let's do that. The LCD, of course, is just going to be the product of these. So I'm going to go ahead and multiply this first one by x squared over x squared. And I'll multiply the second one by x plus h squared over x plus h squared. Again, we're just multiplying by a form of 1, so it changes the appearance but not the value of my expressions. And there's that times 1 over h. So I can now say this is all going to be one big fraction with the denominator x squared, x plus h squared. All right, here I've got 4x squared minus 4 times, and if I'm going to have a hope of simplifying that fraction at all, I know I'm really going to have to square this out. So right here, I'm going to go ahead and I'm going to replace that x plus h squared with the expanded version, x squared plus 2xh plus h squared. That just became this. Right. All right, now the algebra gets pretty routine. I'm going to distribute the negative 4. And as far as the denominator is concerned, clearly I've got that x squared and that x plus h squared. But I could just go ahead and multiply across here and just put that h down in the denominator as well. Won't hurt anything. And x squared, or 4x squared minus 4x squared is 0. And then what I have left here is possible to factor out a 4. I would certainly, excuse me, what I meant to say is it's possible to factor out an h. It certainly is possible to factor out a 4 or even a negative 4 if you wanted to, but my real goal here is to be able to cancel out this h. I'd like to be able to divide that out so that I don't have that 0 in the denominator anymore. So I'm not going to bother factoring out the -4. I'm just going to go ahead and pull out the h. That's what I'm trying to divide out. So factoring out the h from the numerator leaves -8x minus 4h. And now allows me, since I have a fully factored form, to divide those h's, which should get rid of the problem, because I no longer have a factor that goes to 0 in the denominator. So let's plug the h equals 0 in. Numerator would give me -8x minus 0. And the denominator has the x squared, and then x plus 0 squared is just another x squared. So I actually have -8x over x to the 4th, or -8 over x cubed. And that's the derivative of the function 4 over x squared. All right, the second part of this problem asked us to find the equation of the tangent line at the point where x equals 1. So we're done with the part where it said just find the derivative. I now want the tangent line at x equal 1. So let's see. Again, I need a slope and a point. And the slope is just going to be the derivative, but specifically the derivative at the point where x is equal to 1. So if I plug 1 in here, -8 over 1 cubed is going to give me -8. And then my point, again, they already told me they want x equal 1. To get the y value, I'll go back to the original f of x and plug in 1. So 4 over 1 squared gives me 4. And my point is 1, 4. To get the equation of the line, I'm going with y equals mx plus b. Y is 4. M is -8. X is 1. So it looks like I'm going to get 12 for b this time, meaning that my tangent line is y is equal to -8x plus 12. All right, last time we actually started with a graph, and so we already sort of could tell that the line we found was reasonable for that tangent line that we had already drawn on our curve. But this time, since we haven't drawn yet, let's go ahead and go over to Desmos, and I'm going to graph both the original function, 4 over x squared, and then I'm also going to graph this tangent line, and I'm hoping we're going to be able to see that the line that we found really is tangent to the curve. It's a good way to check these problems. So here we are over in our Desmos graph, and notice I've already graphed the original function, y is equal to 4 over x squared. If I add a new graph for the tangent line, which we just found, y is equal to -8x plus 12, you can now see that right here at that point 1, 4, the point where x equals 1 is the point of tangency. That blue line, the tangent line, does appear to just touch our curve at the point. It doesn't seem to cut through 2 points, it just seems to just touch or skim along the curve right there. So it certainly seems to be a reasonable equation for the tangent line that we were supposed to find. All right, let's go ahead and try one more example. This time my function is f of x equals x cubed minus 2x. And again, my first goal is just to find the derivative, f prime of x. We'll use our definition to do that. And then in part B, we'll find the equation of a tangent line. So f prime of x Once again, I'm going to start with the limit as h goes to 0 of f of x plus h minus f of x over h. And the main reason I wanted to do this one was just to remind you that when x appears in more than one place, make sure that when you do f of x plus h, you substitute that x plus h in for both of the x's. So I'd have the limit as h goes to 0 of x plus h cubed, subtract 2 times x plus h, and then subtracting f of x. Again, when there's more than one term, parentheses are super important. I got to subtract the whole thing, so I'm going to put it in parentheses, x cubed minus 2x, so I don't forget to distribute that negative sign in the next step. It's all divided by h. I didn't need my little trick this time since I don't have a complex fraction. I'll just leave the h right down there. And let's see here. This one, there's going to be some significant algebra to do, right? In order to do any simplifying on the top, I'm going to have to multiply this out, as well as the simpler steps of just distributing. So x plus h cubed. Just to save myself a little space, I'm going to go ahead and kind of do that on a separate sheet of paper. We'll plug it in here in just a minute. But if I would like to find x plus h cubed, that means take x plus h times x plus h squared, right? And x plus h squared, I know that one is x squared plus 2xh plus h squared. And I'm going to first distribute the x cubed plus 2x squared h plus xh squared. And then I'll distribute the h plus hx squared plus 2xh squared plus h cubed. And it looks like I do have some like terms. Those two both have an h and an x squared in them. And then these two both have an x and an h squared in them. So combining my like terms, x cubed plus 3x squared h plus 3xh squared plus h cubed. If you remember your binomial theorem, perhaps from a pre-calc class in Pascal's triangle, you may actually be able to use a little bit of a shortcut to get there. If you don't remember those or they don't sound familiar, we're actually going to talk about them a couple of sections from now, so hang in there, we'll get there. But for right now, I'm just going to go ahead and take all of this and plug it in for the x plus h cubed. So this became x cubed plus 3x squared h plus 3xh squared plus h cubed. All right, the rest of the algebra is a lot easier than that, or at least not that that was so difficult, I guess, but a lot less time consuming than that. Distributing the negative 2, I have negative 2x minus 2h. And distributing the negative here, I'd have a negative x cubed and a plus 2x. Once again, this is the point where hopefully we start to see some things that add up to 0 and go away, and we do. Right? X cubed minus x cubed is 0. Negative 2x and positive 2x is 0. And all of the terms that are left have an h in them. So in my next step, I'm going to factor that h out of the numerator. When I see that, I know I'm going in the right direction, because ultimately I want to use that h to divide out the denominator. So 3x squared plus 3xh to the first plus h to the second Oops, you know what? I lost a piece, didn't I? This minus 2h right here. When I factor the h out, I should have had a minus 2 there. So let me fix that. There, that's better. All right, now 1, 2, 3, 4 terms. 1, 2, 3, 4 terms. I got them all. All right. I can divide out the h's now. And since there's no longer a 0 in the denominator, it's probably safe to plug in the h equals 0. So I'm going to get 3x squared plus 3x times 0 plus 0 squared minus 2, which just gives me 3x squared minus 2. So that's my derivative function, and it can now be used to find the slope of the tangent line at any x value. In part B, we specifically are told that we would like to know at what points on the graph would the tangent line be horizontal, and then find the equations of those tangent lines. Well, let's see. I know that anytime I have a horizontal line, the slope is going to be 0, right? All horizontal lines have a slope of 0. So if the slope of the tangent line has to be 0, and I know that the slope of the tangent line is the derivative, what this amounts to is setting this 3x squared minus 2 equal to 0. So let's see, solving for x here, I'd have x squared equals 2/3. So x will be plus or minus the square root of 2/3. That gives me the x values. I'm going to go ahead and get some decimal approximations here. Square root of 2/3 is about 0.816. So that gives me the x values, where I'd have the horizontal tangent lines. If I want the actual points on the graph, I can plug those x's back into the original function and get y values as well. So I'd have plus or minus 0.816 cubed minus 2 times plus or minus 0.816. And let's see, when I did the positive 0.816, I actually ended up with a negative 1.0888, I guess. And when I used the negative 0.816, turned out positive 1.088. So there are the points where the tangent line is horizontal. As far as the equations of those horizontal tangent lines, the equation of a horizontal line is just y equals something, right? So y equals negative 1.088 and y equals positive 1.088. Those two horizontal lines should be tangent to our graph. And that would be the equations of those tangent lines. Let's look at Desmos one more time and see what these graphs look like. So my original function this time was y equals x cubed minus 2x. And I don't necessarily have the best window, so let's fix that. Doesn't have to be real huge. Let's go negative 5 to 5 on both axes. There, that's a little bit better. You can clearly see right here where the graph actually has a maximum, right? There would be a horizontal tangent line. And the same thing down here. Now notice that the y value here is actually 1.089. That's probably a little bit more accurate. I plugged in the decimal approximations, 0.816, rather than the exact value of square root 2/3. So their 1.089 is probably a little bit more accurate than my 1.088. If I graph the two tangent lines, y equals, and I might as well use theirs, 1.089, and y equals 1.0 or negative 1.089. I'll make that one red also. There we go. You can certainly see here that tangent line is just balanced right at the vertex, or the maximum point, and this horizontal tangent line is just balanced right here at the minimum point. The idea that the tangent lines are horizontal at a maximum point and a minimum point is something to note here, and it's something that we're going to bring back and we're going to use it quite a bit later on in the course. All right, that brings us to the end of topic A.